Hey, Mike.
Morning, Doc.
So into the black hole today. Then we have to abandon our, we're going to look at more the short shared coordinates. You'll see that they're not the best. And so we have to get rid of them. And that's going to be our request to get the crucial coordinates. And that's, so we'll have a very broad view of our black hole next week. Very, very broad. And it's going to predict some things. Okay. So we were talking about a radial plunge into a black hole. From the perspective of the one falling into black hole. And from an outside observer. So you said here's, let's say here's your black hole. So this is your short shared radius. Here you are here. So here's going to be, these are outside observers. And then we have a little ship here like this. Somebody going straight into the black hole like this. So we did it from this person's point of view, and then we're going to start from this person's point of view here. And so from this person's point of view, what did we find? We found that basically you don't even notice anything when you cross the event horizon. This is your event horizon, and it takes a finite amount of time to actually hit the singularity. Let's set up the equations because we're going to need them again. So how did we go about doing this? To do these calculations, we need, the first is the epsilon. We have the epsilon, which is this minus k mu u mu. And we worked out that. This ended up giving us this 1 minus rs over r dct d tau. And we set up the object is basically at rest far away. We could look at far away. So if far away, so let's actually use grammar good me speak. If the object is at rest, when it is far away, we show that epsilon equals c. So the c's cancel. So this is one of the equations we need. We have this dt d tau equals 1 over 1 minus rs over r. So everyone happy with that? Then we got the other one from the orbit equation. So this is one equation. Okay, the other equation comes from the orbit equation. And that gave us this, we had this epsilon squared minus c squared over 2 equals 1 minus here. Here where L equals 0 and theta and phi are fixed. And in this case here, then this goes off to 0. So this whole thing here equals 0. So that equation, if we solve for it, gives us dr dt, or dr d tau, equals plus or minus the square root of 2gm over r. Does that make sense? Okay, let's make that look a little more in terms of the short radius. What are we missing here? In terms of a short radius? Remember, the short radius is 2gm over c squared. So what I'm going to do here? Multiply top and bottom by c and take one of the c's in here. So if I do this, we didn't do this yesterday, well, we're going to today. I take this guy into here, and this is going to be plus or minus c square root rs over r. That's fine. Okay, so to do this guy here, what did we solve to find the equation for this one here? This one is pretty simple. Then what did we do? If you want to find it from this person's point of view, how did we deal with this? What do we have to look at? From this point of view, you're looking at your watt, so you're measuring what? Proper time. So in this case, all we had to do is solve this. Okay. So in that case, okay, from the perspective of the unfortunate soul, soul falling into the black hole. All we had to do was solve this guy here. So we took the square root of r to the side here. We had a minus here, and then the c over here. Here's the square root of this rs. Here's that c, and here's your d tau. And then we integrated this, and then we get a finite time. Now, why did I use this minus sign here? Because you have a plus and minus here. We said when we do it though, we're going to keep a minus sign.
Because dr is in the negative radial direction.
Exactly. Your dr is actually decreasing because we're falling into it. The d tau is positive because time is increasing. This gives us a finite tau. That all fine? Okay. Now, from this point of view, from the perspective of an outside observer, what we do is that instead of having dr d tau, we're going to have dr dt. So from this person's point of view. Okay, so any questions to this? This is what we did last time. Okay. And you can see it's really simple. Okay, so from perspective, the outside observer, we need dr or dr dt, it doesn't matter which way you do it. And we mentioned last time how we do it. We said that if we look at dt d tau divided by dr d tau, right? What does that equal? Well, this is really dt dr. But what do you know? We actually have this. It's our friend over there. And we have this. It's our friend over here. So now we're going to just put everything in here. So dt dr equals, okay, our friend here is the boxed in equation up there. Sometimes you just feel boxed in life. It means you're an equation. Okay. So we got that guy divided by, and now we're going to take our little friend here. I'm going to keep the minus sign because we're still going to be falling into our black hole. Like that. That looks kind of yucky. Let's make that look pretty. I didn't make any copying mistakes, did I? How could I possibly make a copying mistake? So let's clean that up. And that gives us the TDR equals minus. Okay, here's a C. So this is going to be 1 over the square root of RS over R. This will be a minus C here. And 1 minus RS over R. Okay, so the equation of this is actually listed in that handout. So if you look at that handout, if you look at the equation 1617 is a solution to that. I'll probably have you work it out as homework and stuff like this. It turns out to be really kind of delicious. The claim is that I'm going to show you qualitatively why this is true, but I'm going to really concentrate on one part here. If you solve this, you obtain. So here's your T, here's your R, here's your short radius. This guy gives us this. So this is our R naught value. Okay. Remember, R naught is the integration constant we had here. So we're starting at some R naught here. You have something like this. So this is basically the this is the proper time calculation. So basically, nothing funny happens at the short radius, and you just smash into the singularity and get shorted. From this point of view, what you're going to find out is that this is going to go like. That's what this one here gives. Okay, this is from the outside. This is from the outside observer. So again, if you run away from home stealing your current spaceship, you go and smash into the black hole and get shredded. Your parents will only see you here. They're going to see you on the edge of the event horizon. You're never going to cross, and you're going to be there for the rest of your life, as far as their perspective is. Okay, so what I want to do is, okay, I'm going to have you work out that form here in homework. Now I'll lead you through the integrals. Now it's one of those where it's a quest. The part where I want to work out in class is I want to work out this part here because it's ridiculously clever. It's not, there's a trick. Again, if somebody didn't tell me the trick, I would have never saw it. There's a beautiful trick for it. What I want to do is work out this part here. I want to convince you that this equation here would never allow you to cross that boundary. I want to show you what that is. So what I want to do is analyze this equation here for the case where R is really, really close to the short radius. And there's a trick. The substitute, you have one substitution, and once you do the substitution, everything comes through brilliantly. So we want to ask, we want to show that the equation that the solution for the dt dr equation never crosses the R equals equals RS line. Okay, so you never cross your Church radius from this perspective here. But I wanted to show you how that works. So does everyone understand what we're going to do? Okay, to do this, we're going to use a trick. I'm going to use the following clever trick. Then Vernal, where I got that handout from that I gave you, actually has this as a homework assignment. But he states the trick to use. Here, I'm just going to do it. I was thinking about making it a homework assignment, but it's just so elegant. I want to do it here in front of you. Okay, so we're going to do the following first of all. You're going to rewrite TDR. And the way I'm going to do this is I'm going to come down here to this piece here. I'm going to factor out a piece of minus RS over R. I'm going to factor that out. So we're going to rewrite this by factoring out a minus RS over R in the denominator. So for factor, okay, I'll write this. 1 over C square root of RS over R. And pull out a minus RS over R. You tell me what we're left with.
Minus R over RS
Okay, so here,
plus 1.
plus 1. Okay, let's rewrite this now. So I'm going to minus signs will cancel. These two terms I can write as this. I can write this as the square. I can write this as 1 over C RS over R to the 3 has power. 1 minus R over RS. Now here's the trick. Okay, already this. Okay, you don't have to do this part wasn't in this trick, but I think it simplifies things. You let this quantity here. Okay, R is going to get near R sub S. So this quantity here, this whole quantity here is going to be small. Okay. So what we're going to do is we're going to let 1 minus R over R S here be by definition delta. Note, when R approaches R sub S, delta goes to 0. And this is the only region we're interested in. So let's make this substitution. dr d tau dt dr equals. Okay, so if we solve this here, I can write this also as, I can take this over here, I can say this is R over RS equals 1 minus delta. So what does this give us? This, oh, yell at me here. No, don't yell at me. I looked at the wrong equation. I'm right. Woohoo. Okay. 1 over C. What does it? Okay, I'll do this term over here. Delta. This is just delta. What does this term over here become?
1 minus delta to the 3 halves.
Yeah, this term over here just becomes.
Oh, wait.
This is actually just a reciprocal of this.
Okay.
1 over 1 minus delta. Okay. So let's rewrite this. This gives me dt dr equals 1 over C delta 1. Okay, 1 minus delta to the 3/2 power over C delta. Again, we're only interested in this as R approaches R sub S. What are we going to do to this crazy term? No. Yes. No. Yes, we're going to do binomial expansion. You got 1 over C delta. You're going to binomial expand this. Okay, so what is the leading order term then? The leading order term is 1 over delta. So this is 1 over C here. This is the leading order term. Okay, as R goes to RS. What is our friend delta? Right here. So as R goes to RS, we can state that dt dr is 1 over C 1 minus R over RS. Hey, what can I do with that? That's just a standard integral. I take the C over here to have distance units. I'll take the dr over here. So I'll write this as C dt equals dr. Here. We integrate both sides. I'm going to say from some t prime to t. T prime is going to be near R equals RS. So, if I were to, this would be from like R prime to R. So what I have here, this is my RS here. And say R prime is kind of here. Because we're integrating along this little region here. We don't care about this stuff over here. We're only interested in this little region here. Okay. I'll do this side for you. It turns out the integral of dt is t. If I put in the upper limit and the lower limit, this left side becomes c t minus t prime equals. You tell me what the right side becomes. What is this guy? Don't make me get the white fluffy cat. Delay.
Oh, no.
Yes, there is an ln. ln of 1 minus R over RS. What goes in the front? Which R? The RS. So tell me what to put in front of here. There is a minus.
RS?
RS. Right? If you differentiate this, what do? You take this and put it in the bottom. So that goes into the bottom here. And then you have to take the derivative of this and put it in the numerator, which is a minus 1 over RS, which cancels that here. And then this gets evaluated on R prime and R. Okay, so what do you get? I'll take this over here. Put in the upper and lower limits here. what happens?
Get a ratio of the arguments in the logs.
Now what? Exponentiate both sides. And then take over this guy here. So this goes 1 minus r over rs prime, e to the minus c, t minus g prime over rs equals 1 minus r over rs, multiplied by rs. Okay. The question is basically, here's your R and here's your RS. The question is, does this ever go to 0? Look at this. This is finite. Okay. Here you have an e to the minus something with a t in here. As this t increases, what happens with this term here? It gets smaller. It asymptotically goes to 0. This term never equals 0. It asymptotically goes to 0. And that's why this curve here, when it comes in like this, asymptotically goes to 0. I mean, it asymptotically gets closer and closer and closer and closer. It never crosses it, as you can see here, it never does. It's really slick. I think that's a terribly clever argument. Does that make sense? So this, as t goes off to infinity, r minus r here never equals 0. So you never actually hit this line here. You get asymptotically close to it. So as far as your parents are concerned, you're at the edge of the event horizon deciding what to do. And they're waiting for you. Like, I know Junior will come home soon. We didn't raise a fool. They'll turn around the spaceship. I know they will. Questions? Okay, let's go through and I want to analyze this kind of what's going on here. It has to do with the light rays. So we did part of this the first time I kind of introduced black holes kind of mamby-pamby. I want to make it more rigorous. And you'll kind of understand what's going on with this, why you're going to get this effect. And then also what you're going to see is it's going to show us why we need different coordinates. Because it turns out that these, the short coordinates we're using are just crappy coordinates. They're fine over here, but as you start getting toward here, they start getting funky. And they don't even really work well here at all. And so you like to have coordinates that allow us to go all the way through here like this. Really good coordinates. And not just that, we ultimately want to get really good coordinates. What is the time dependence? What kind of black hole are we assuming? We're assuming static. What does static mean? Okay, it's not rotating, something else. What happens if I replace t with minus t? Be no effect. If it's truly static, there's no time dependence. So I can let t go to minus t. So we're ultimately going to switch the coordinates that they're even going to allow us to explore kind of like in the past. It turns out that when we go to those coordinates, they're going to be the crucial coordinates. We're going to be able to go into here. We're going to be able to go into the past. We're going to be able to explore all the possible spaces of this. And you're going to get predictions. We're going to get the whole idea of a white hole. And it turns out there's going to be a whole nother universe that we can't have access to. There's a wormhole connecting the two. And we'll see where that comes from. But you can never get it. You can never get there. It turns out that as you go, the wormhole's open as long as you're far away. But when you start getting closer to the wormhole, it shuts up on you. So you can never get there. So you can never have access to that other universe, okay, or to that other regional space. And it's going to all be quite explicit. It's quite beautiful. Okay, but we're not there yet. Let's reanalyze this from the light point of view. So let's ask, let's analyze this problem from the point of view, from the light poles. Okay, so I write down our metric like this. There's a whole metric here. If you want to analyze light, what do you do to this equation? We didn't know about TS squared for light. It's 0. So for light, TS squared equals 0. And also we're still having, we keep theta and phi fixed. So let's analyze this, and we've seen this before, but I did it was really, really fast. Okay, so what do you get? You get 0 equals 1 minus RS over R, C squared dt squared plus dr squared over 1 minus RS over R. Now I want to get dt dr.
Is there not a minus sign on that leading term?
Thank you. That'll make a difference. So I take this over here, and this is going to give me this c squared dt squared equals. I'll take the dr over here. Let's just fix steps. Okay, and take the dr squared over here, this over here, and take the square root. So this is going to be this, plus or minus square root of, this is over dr. Taking the square root kills that part there. This. Does that make sense? No, I started to write when I don't know why, because I was taking the square root of both sides because I'm dumb. So you take this over here, that makes this squared. This whole thing here is squared, and so you take the square root of the whole thing. So you have something like this. You have c squared t squared dr squared equals 1 over 1 minus rs over r. Then take the square root of that. Okay. So what is this going to be? These are going to be how the slope of the light line. So we're going to draw basically our t versus r diagram. If you look at your t versus r diagram, so this is CT, that C is going to go away. This is R. Here's RS. So am I still on the camera mic here?
Yeah, you're good.
Okay. So if I'm right here, let's say this is far away. What does that equation give me? Well, let's say we're over here, the R is much greater than RS. What does that tell you about that? CD dt here over dr equals plus or minus 1. Right, because this is large compared to here, so that goes out, so I get plus or minus 1. So I can have a light ray like this. That'd be an ingoing light ray. Okay. Or I can have a light ray like this. This would be an outgoing light ray. So again, remember what you're doing here. That means if here's your event horizon. Here's your R coordinate here. We're way out over here. I can either send light this way, that could be light, or I could send light this way. We're looking at radial light. So we're looking at radial light going in or radial light going out. So if it's going in, it's like this. If it's going out, it's like that. Does that make sense? Now, what happens though as you get closer and closer and closer and closer here? So as R gets closer to R sub S, what happens here? Yeah, we're still over here that we're still, so R is still greater than R sub S. This approaches this. This gets closer to 1. 1 minus 1 is closer to 0. Okay, or we should say 1 minus something closer to 1. It's getting closer to 0. 1 over something closer to 0 is something large. Okay, so you start getting a steeper slope. So what happens is as you go closer and closer and closer and closer here, this light cone actually starts closing up more. It goes like this. It goes like this. Then if you get really, really close here, how does it look? If you get really, really close here, you basically have almost 2 vertical lines here. Okay. Does that make sense? So where am I? Let's put it over here because you're getting close to the edge. And so let's say here's mom and dad. Okay, they're at some fixed star here. If junior is over here, okay, if junior is over here just stationary here, what's going to happen? If junior is just stationary, so this is a stationary junior. Okay, and then send light signals. What does happen here? If you're really, really far away here, so let's say this is R much greater than R sub S. These light rays are just going to go like that. You can communicate fine with mom and dad. Okay. But as you get closer to here, let's say our junior is here. Let's say stationary. Okay, still stationary. How do those light rays now look? Now here they're going to be a lot more, they're not going to come out at this 45-degree angle because that was 1, so it's 45. It's going to come out a lot more steep like that. Now how's this going to actually change though, the further you go out? As that light ray is here, what happens to the light cone? It bends a little bit more, then it bends out like this. So this isn't going to go into some straight line like this. This is actually going to go in kind of arc, kind of a funny fashion. Does that make sense? So what's going to happen here is that these things here are going to come out and they're going to kind of arc like this. And then if it's here, it's going to arc like that. And there's one of the handouts I gave you. I don't know if it's the same one. Okay, I gave you one a long time ago. That looked like basically you have a ship falling in here like this. And that ship as it's going out is sending out beacons. Okay, so if you look at basically the here's your R, here's your CT. Okay, so let's say this is a ship from the parent's perspective here, like this. The graph we just worked out. So this would be the TDR for a ship rarely falling in. As seen by an outside observer. This is that graph we just worked, that you're going to do the integral for it. We did that part close here. But this person is sending out standard signals. And if you look here, there's kind of signals here. So they send out a signal here at this point, they send out a signal here. So this region right here, the proper time interval between these are the same. When you actually go through and work this out, so here are your parents like this. If this is the light signal here, that light signal is going to come up in here like this. This light signal is going to come up here and out like this. The reason why is because this initial slope here and this initial slope here are different. This one here, that initial slope is like that, so that one's going to go out like this. So the further out what happens is the further you get in here like this, the distance between these signals being sent get larger and larger and larger, and that graph shows it actually quite nicely. Does that make sense? Now, What happens over when you get really, really close here? So here you are in the ship here like this. Now you send out a signal. How do the light rays look here? This graph really, the light graph really shortens up like this. So in a case like this, these light rays now look like this. So the light ray here is going to go like this. And go up a lot further like that. And if you get really, really close, asymptotically close, these light rays are actually vertical lines. And so those vertical lines are going, that light rays are going to go up like that. They'll hit the parent off at infinity. So you're never going to see them. The parents are only going to see you here. That's why that's happening. Does that make sense? Questions of that? Ask away. Anything?
So if you had like the parents come in at a later time, if they approach the black hole, would they see you go into it when they cross the horizon?
When they eventually, if your parents call and then stupidly cross here, they're gonna, they're gonna see your shattered ship here. Like, oh, that's bad. Okay, I guess Junior wasn't hanging out here. But they get really, really close here. So let's say they come out here and then hang out. That would be their line here like that. So they're still gonna see, actually, depending on how close this is and how close they are here, they're still gonna see those lines are gonna go like that. They're still gonna see you still stuck here. Because they're still in this place. Okay. Very cool. Now you can actually see something else here. You can actually kind of figure out that graph. So if you look at that one, so for the homework, you're going to work out this graph here like this. Okay, so that one we worked out. Then I said for homework, you're going to work out this guy like this. You can qualitatively understand this graph here like this. Let me kind of qualitatively explain this graph here. If you go over to here, let's look at our light curves. So what we want to do is we want qualitative understanding of the dTdr for the falling observer, for the observer, for the ship falling into the black hole. It's actually kind of easy to understand qualitatively. So let's say here's this, here's this, here's this. If I'm far away, here's your light cone. So this is the light cone. How would any person moving in here? How would that ship have to go if they're moving here? Where the ship you can find? That ship velocity would be confined within the light cone. So if you're traveling this way, you could go like this, right? You can't be like that. You'd have to be within the light cone. When you get over here, so now let's say you're here, right? Because you're moving this way, so time is increased. So now you're here, how does that light cone look? That light cone here looks like this. So where does the velocity of your ship have to be confined? Within the light cone. So now maybe the velocity of your ship is like this. Okay. So now let's say you're here. So now you're someplace up here. Now that light cone looks like this. And now the velocity of your ship has to be confined within that light cone here. And that's why you're getting this kind of snaking behavior like this. Because you always have to be within that light cone. Does that make sense?
Does that mean that your like approaching C.
No, because you're not exceeding this part here, no matter what. You're still within that time. So what we're gonna do on Monday is we don't like these coordinates. We want something that's actually better behaved here at this spot. Because at this spot here, the G's aren't even well defined. It has to do with the coordinates. So what we want to do is actually shift coordinates. And we're gonna first of all on Monday. So on Monday, we will switch to the Eddington. Here's the next great name, Finkelstein. Okay, I think if your name's Finkelstein, you get made fun of a lot as a kid. I just think you would just. Yeah, yes. So anything Finkelstein coordinates. And that's going to fix some of the problems here. But it's not going to be perfect. And so this will be our first step. So we do this on Monday. We'll see how that works. And then what we're going to do is on Tuesday, Wednesday is off. Wednesday's our break day next week. And so on Friday, then it'll probably be like a 2-day event to switch to the crucial coordinates and then see how the whole thing works. So I'm hoping by Friday, we're going to have the entire stationary black hole mapped out. And the week after that, we then set the Kerr black hole. And then after that, cosmology. Okay, have a great day.
Awesome. Thank you.
Take care.